Hello everyone. This is part 2 of section 14.5, the chain rule. Last time we left off with an example of the chain rule that was a function of w expressed in terms of x, y, and z, where x, y, and z were just all explicitly functions of t. So we saw our little tree diagram here on how to generate the formula, and the formula stated, and just went ahead and plugged in, calculated the respective partial derivatives and derivatives, and just simply plugged into the formula and made sure we were in terms of the variable t at the end here. So when we had the x and the z and the y, we substituted literally the equations for those in terms of t. So now we extend this to what we call the two-variable chain rule, and with that we have our formulas, but now we have that x and y are functions of two variables, and then we have a function z that's a function of x and y. So if we start with z in terms of generating the formulas, it's a function of two variables, so we can extend that to x and y. So, and because it's a function of two variables, these would be the partial of z with respect to x and the partial of z with respect to y. But then x and y are both functions of u and v. So those would be partial derivatives as well. So the partial of x with respect to u and the partial of x with respect to v. And similarly for y, it's a function of u and v, so partials as well. So partial of y now with respect to u, and partial of y with respect to v. So let's say our main goal is to get to the partial of z with respect to u. We'd be following this first branch and the third branch to get to the u. So following the branches, the partial of z with respect to u is partial of z with respect to x, it's the first branch, and then times the partial of x with respect to u, and then plus. So you can see how you can almost think that the partial of x is canceled, but we know that's not what's happening. But then plus, similarly, to get to this branch, partial of z with respect to y, and then times partial of y with respect to u. And that's our first formula. And you can verify the second in a similar way. So now getting to the example, we have to find both partials, and so it looks like we're going to need partial of z with respect to both x and y. So the partial of z with respect to x is, ky is held as a constant, and the derivative of x squared is just 2x. Partial of z with respect to y. X is held as a constant, and derivative of x squared is 0, derivative of 2y is 2. Okay, then we're going to need the partials of x and y. To do both of them, partial of z with respect to u and v, we're going to need partials of x and y both with respect to u and v as well. So the partial of x with respect to u is 2, because v is held as a constant. Partial of x with respect to v is 1, because u is held as a constant, and the derivative to u would be 0. Now for the y, partial of y with respect to u would be 2 again, and the partial of y with respect to v is -1. Okay, so now for the actual partial of z with respect to u, I'll write out the formula. Partial of z with respect to x times partial of x with respect to u plus partial of z with respect to y times partial of y with respect to u. So we get 2x times 2, and then plus partial z with respect to y, that's right here, this 2, times partial y with respect to u is this 2. So we get 4x plus 4. But the question did ask to give the results in terms of u and v, so replace x. So we get 4 times 2u plus v plus 4, and then just distributing, we get 8u plus 4v plus 4. Okay, so then finishing it off, partial of z with respect to v is going to be found in a similar way. Let's write the formula. Partial of z with respect to x times partial of x with respect to v now, plus partial of z with respect to y times the partial of y with respect to, again, v. So going back up here, got the 2x again, times, now the partial of x with respect to v was this 1 right here, and then plus partial of z with respect to y was this 2, and then times partial y with respect to v was the -1. So we get 2x minus 2, and again, replace the x by what it was defined to be in terms of u and v. So we get 2 times the quantity, 2u plus v, so 4u plus 2v minus 2. Okay, so now we move to one final concept in this section, and that is implicit differentiation. And with implicit differentiation, recall from Calculus 1, for example, let's say you had to take the derivative with respect to x of x to the 5th. Well, we just differentiate as normal, we get 5x to the 4th, and that's all there is to it. But if you have to differentiate, let's say, with respect to x, y to the 5th, then recall that because we're assuming y is a differentiable function of x, and I'm just going to try to adjust the focus here. Okay. Assuming y is a differentiable function of x, when we take its derivative, well, we get 5y to the 4th as normal, but if we're differentiating implicitly with respect to x, recall we have to include a factor that represents the derivative of y with respect to x, where we'll denote that by dy dx. And then anytime you differentiate with respect to a variable that's different from the independent variable you're differentiating with respect to, like you could have the derivative with respect to, let's say, y of z to the 5th, and then you get 5z to the 4th, but then times the derivative of z with respect to y. So we'll look at an example here, and this involves the partial differentiation. So we have to keep in mind in this example, when we find the partial of z with respect to y, okay, I always like to kind of write it off to the side so it reminds me of what I'm finding, because it tells me I'm differentiating with respect to y. so x is held as a constant, but z behaves as the function of x and y. So whenever we differentiate z, we're going to need to include the factor that represents the partial of z with respect to y. So when we start the differentiation process, actually let me recopy it. X cubed y minus 5 xy squared plus 3 xyz minus 7 y z squared equaling 0. Okay, so now we start the differentiation process. Excuse me. Now we're differentiating with respect to y. So x is held as a constant. So here the derivative of x cubed y, well, x is a constant, so the derivative of y is 1, so we just get x cubed. For the next term, similarly, x is a constant, so the negative 5x really just tags along. Derivative of y squared is 2y, so that becomes negative 10xy. But now we have to consider in this next term that x is being held as a constant, but y is the variable that we're differentiating with respect to, and z is a function of both x and y. So for this term, we're going to need the product rule. So I'm going to treat the first factor as 3xy, because x is a constant. So I'll have the first 3xy times the derivative of the second, and now that's the partial of z with respect to y. And then plus the second factor. So let me make this plus bigger so that you know these two terms are generated from that product rule. So then plus the second factor z, and then times the derivative of the first. And the derivative of the first, x is a constant, derivative of 3y is 3, so that's just 3x. And then going to this term, well, I've got the negative, and we also have a product of y and z. So this is going to require the product rule as well. Alright, so you can do your algebra any way you want. I'm going to leave the negative, and then I'm just going to use the product rule on the positive 7y z squared. So the first factor is 7y. Derivative of the second, differentiating z squared implicitly with respect to y. Okay, that's why it's helpful to put this off to the side, because now it tells you when you differentiate z squared you get 2z, but then you need the partial of z with respect to y. And then plus the second factor, let me get that parenthesis out of there. And then plus the second factor, let me clean up that z as well. Second factor is z squared, and then times the derivative of the first, and that would just be 7. And that's equal to 0. Okay, I'm going to take a step just to kind of rewrite things, regroup, make them look a little more presentable. So just rewriting everything, putting them in a nice order, and maybe distributing this negative now. 14yz partial z with respect to y, and negative 7z squared is 0. Okay, so then we have to solve for the partial z with respect to y. So everything that contains that we'll leave on the left side. Everything else move to the right side. So I'm indicating with little transposition arrows there. So the 3xy times the partial of z with respect to y, and the negative 14yz times the partial of z with respect to y stays on the left, Everything else moved over, so negative x cubed minus, now that becomes plus 10xy minus 3xz and plus 7z squared. And we'll factor out the partial z with respect to y. And we're left with that times the quantity 3xy minus 14yz equal to, just recopy the right hand side, and now to solve, just simply divide both sides by what's in parentheses on the left. So what's on the right is the numerator of a fraction, and what's on the left in parentheses is the denominator of that fraction. Okay, and then they want us to verify that the formula for dz dy, or the partial z with respect to y, can be thought of as the negative of the partial of f with respect to y over the partial of f with respect to z. And that's where we're considering the function f of x, y, z to be this entire left side of the equation. So let's find these two partials. Partial of f with respect to y would be, okay, so now term by term, let's look at the original. With respect to y, x cubed, x is held as a constant, or the y is 1, so that's just x cubed. Go to the next term, that becomes 2y times negative 5x is negative 10xy. To the next term, z is being held as a constant now, because now we're considering this to be a function of x, y, and z. So x and z are constants, or y is 1, so plus 3xz, and then again z is a constant, so derivative of negative 7y is negative 7, so minus 7, and the z squared tags along. And then similarly we find the partial of f with respect to z, so now x and y are held as constants, so this function is just x and y, so its derivative is 0. Same with this term here, derivative of z is 1, so we get 3xy, and then minus derivative of z squared is 2z times negative 7, so minus 14yz. And then finally we could verify that this is true, because if we consider substituting into the suggested formula, it's saying it should be minus the partial of f with respect to y, which is the x cubed minus 10xy plus 3xz minus 7z squared, all over this 3xy minus 14yz. And that's pretty much sufficient to show, because you could see, but if you wanted to distribute, you could see that everything's the same upon mentally distributing this negative. But if you wanted to distribute that negative literally, negative x cubed plus 10xy minus 3xz, and then plus 7z squared. And now you can see it matches identically. So it's verified. Okay, so that's the end of 12.5. And so whenever you get around to it, I'll see you for section 12.6.